Today, we are diving deep into the hidden architecture of our universe. We're talking about a framework that's so symmetrical, so elegant, it's often just called beautiful. Of course, I'm talking about Maxwell's equations, and we're about to see them in a whole new light. So this right here is the EDBH framework. It's a visual way to look at Maxwell's equations. And you can see it right away, can't you? That beautiful symmetry. The equations arranged diagonally are practically mirror images of each other. Now, this isn't just some pretty pattern. No, it's a huge clue to the fundamental structure of reality itself. So let's unpack what it all means. Here's our game plan for this explainer. We're going to start by bridging the gap between the physics you might remember from high school and the much more powerful ideas used today. We'll explore two key mathematical pillars. That's Gauss's and Stokes' theorems that make everything possible. Then, we'll peek inside this framework at the sources and potentials that actually generate the fields. And we'll finish up with a really powerful technique to make sure you never get lost in the math again. Okay, let's kick things off with a concept that might feel a little familiar from back in the day, Gauss's law. You know, in its simplest form, it seems pretty straightforward. But that simplicity, well, it comes with some pretty big limitations which we're about to tear down. This is probably the version you've seen before. It's nice and clean, right? No messy integrals, just a simple calculation. But here's the catch. This equation only works under a very specific, totally idealized set of hidden conditions. We're talking perfect spherical symmetry, with one single point charge sitting smack dab in the center. The second you change the shape or nudge that charge off center, this simple little formula just completely falls apart. And here you can really see the massive leap we're talking about. On the left, you've got that simplified special case. On the right, you've got the powerful generalized law that works in any situation for any closed surface with any distribution of charge. Yeah, it looks a lot more complex, but its power is just immense. So how in the world do we get from one to the other? Well, the answer lies in this beautiful piece of mathematics called Gauss's theorem, or you might know it as the divergence theorem. This theorem is amazing. It acts like a dimensional bridge. It's the mathematical backbone that connects what's happening on a two-dimensional surface, like the total electric flux passing through it, to what's causing it all inside the three-dimensional volume that the surface encloses. At the very heart of this is the concept of divergence. The best way to think of it is as the outflow or the emergence of a field from a single point. You know, a positive charge has field lines just flowing out from it, right? Well, divergence is just the mathematical tool we use to precisely measure that outflow at any point in space. And what's the source of this outflow? It's the charge density. Now, this slide highlights a really crucial difference. The integral form gives us the big picture. The total flux going out equals the total charge inside. Simple enough. But the differential form, oh, that's way more powerful. It gives us the precise relationship between the field and the charge at every single point in space. It's like knowing the microscopic rule that creates the giant macroscopic effect. So, we've built our first dimensional bridge for electric fields, connecting a 2D surface to a 3D volume. Now, let's switch gears and turn our attention to magnetism. It needs a different kind of bridge and a totally different kind of source. So if divergence is all about outflow, then for magnetic fields, the key idea is something called curl. The best way to picture curl as a vortex. Just imagine the magnetic field swirling around a wire that's carrying a current. The curl is what measures the intensity and the direction of that vortex-like behavior. It's our mathematical tool for describing fields that circulate and swirl. And hey, just like with Gauss's law, our understanding of magnetism evolved in stages. We start with that simple high school case for a long, straight wire. Then, using Stokes' theorem, that's our new bridge connecting a 1D line to a 2D surface, we generalize it. But the story was not complete. Not until the great James Clerk Maxwell added his famous displacement current term. And believe me, this wasn't some minor tweak. It was the key that unlocked the very existence of electromagnetic waves and unified electricity and magnetism forever. All right, we've now established the mathematical framework on the outside of our EDBH diagram. So now let's actually venture into the inner world and try to understand the fundamental sources that create all of this beautiful structure in the first place. You know, everything we've talked about originates from just two fundamental sources. First up, you have charge density, which creates our emerging electric fields. And second, you have current density, the source of our vortex-like magnetic fields. And crucially, there's a feedback loop. The fields, once they're created, exert the Lorentz force back on those sources. It's this elegant little dance that governs everything in electromagnetism. Physicists, they're always looking for deeper, more unified concepts. And that's exactly where potentials come in. Think of them as the source code for the fields. The scalar potential and the vector potential are these mathematical ideas that provide a more fundamental origin point for both the electric and magnetic fields. And they live right here inside our EDBH framework, representing the unified source from which all the fields emerge. But what's really incredible is how these potentials connect back to our original sources. Under static, unchanging conditions, both of these relationships are described by an equation with the exact same mathematical form. Just look at that structural similarity. It's another powerful hint at the deep underlying symmetry of electromagnetism. The physics for both electric and magnetic potentials follows the exact same elegant mathematical rule. This framework also allows for this wonderfully neat way of organizing everything. We can basically classify every physical quantity into one of two families: the ampere system in green, which includes things like current and magnetic field strength, and the volt system in red, which includes voltage and electric field. The key insight here is the rule for energy. You always get energy density by multiplying something from the volt system with something from the ampere system. It's always a cross-system interaction. Pretty cool, huh? Wow, okay, this has been a lot of theory, a lot of abstraction. So to wrap things up, let's talk about a practical, powerful tool you can actually use to navigate all these equations with confidence. This is what our source material calls the ultimate self-defense technique. The technique is called Trinity memorization, and it's really just a simple three-point check. Whenever you're working with an equation, just ask yourself these three questions. First, is it theoretically rational? Like, does it actually make physical sense? Second, is it mathematically consistent? Are you using the right operations? And third, and this is a big one, do the units on both sides of the equation match? If all three of those things align, you can be pretty confident in your work. I absolutely love this quote from the source material. It reframes checking your units from, a boring chore into an active self-defense technique. Units aren't just bookkeeping. They're your single best friend for making sure your understanding of the physics is actually correct. It's the most practical, most powerful check you have. So, let's bring it all home. Mathematical theorems like Gauss's and Stokes, they're the skeleton that our physical laws are built on. The fundamental sources, charge and current, can be abstracted into potentials, which reveals a deeper, more elegant structure. Remember that the local differential form of a law is always more informative than the big picture integral form. And most practically of all, always, always check your units. And that brings us to our final thought. We've seen how this desire for unification and symmetry led Maxwell to unify electricity and magnetism into this single, beautiful framework. It really leaves us with a question, doesn't it? What other forces of nature might one day be unified by revealing an even deeper, even more elegant mathematical structure?